Section 5, medical applications here, and since one of the focuses of this course, and specifically its sequel course, is for the emphasis is for those of you going into medical fields, this is a good overview and application section. Because it is an application section, though, it's going to be a lot of reading and just straight up text here, and not a lot of elaboration from me. I will point out that this is just a wonderful diagram that just shows all the different radioisotopes, or some of the different radioisotopes at least, that could be used for treating different diseases, different cancers especially, in different areas of the body. We can also use radiation for scans and imaging, as has been mentioned before, so we're going to go into that. So the big thing is when we're using them in medicine, we want short half-lives, because the body can't tell the difference, and so the body will, as I've described previously, end up incorporating the radioactive or non-radioactive versions into itself. If you need a element like iodine in your diet, then that iodine can be radioactive or non-radioactive. Because of that, the radioactive version can be damaging if you end up absorbing it. And so one of the reasons we want short half-lives is if we are using it to treat something, we want it to decay away quickly. In addition to that, the short half-lives allows the damage that can be caused by these to be short term. The other one that they don't really list here is short half-lives usually work faster, because they decay faster, and so they emit radiation faster, and so then you can get through the treatment faster. You can limit the damage to the healthy cells, the good cells, by having the radioisotope get flushed out very quickly, because it's no longer around, because it's decayed into something else. I will clarify here as well that we don't just have to be concerned about radioactive isotopes of, say, iodine, where we have the dangerous version and the not dangerous version. Anything that is in the same family on the periodic table. I believe I mentioned this when we were covering periodic table. Because they're in the same family, they behave similarly. So it turns out that calcium is what your body needs for strong bones, but it also turns out that strontium is in the same family. It's also an alkaline earth metal, and there are radioactive versions of strontium. And so your body actually can't distinguish between some elements that behave similarly that are part of the same family. And so what can happen is from nuclear fallout, you can end up having your body incorporate strontium into the bones, and bone cells take a long while to be replaced. And so then that strontium just stays there and keeps irradiating your body and can cause long-term health effects as well. So there can be, as we've said a few times before, both benefits and damage from radioisotopes. And so it makes it very important to make sure that we're picking the right ones. Anyway, here are a list of some radioisotopes that are used and some of the different applications that they are used in. I will point out that the half-lives here are given to you, and most of those half-lives are relatively short. We don't have any that are getting up into years there, and they all emit different types of radiation. Again, it's great practice to go through and use these and do nuclear reaction equations for them, but we're going to move into just a example question here. Which of these are most likely to be used in nuclear medicine? Well, we want things with short half-lives. This one here, definitely not. It's going to take it 1 billion years to be active. You're going to be gone before that. If you didn't catch it, there's just a jump on the screen. I paused it and fixed a typo that was here. If you're using the printout of the notes, it probably still has the typo, but this is supposed to be potassium-42. Potassium-42 has a short half-life. That one is definitely used. You can go back to the table and see it as well, but iodine-131 is used. 8 days is still relatively short, and so then those are, can be, I should say, useful for nuclear medicine, and you'll see that they are on that table there and have uses already. So we can also do scans with radioisotopes. What we do is we just give you the radioisotope to consume. Sometimes and you're swallowing it. Other times we will inject it into the bloodstream, or it'll be some other kind of injection. But what we can do then is the radioactive isotope will be incorporated into the relevant part of the body. The next example here on the following slide shows iodine-131 used in detecting the thyroid. Iodine in your body is used in the thyroid, so if we give you a radioactive iodine, it's going to go through the thyroid. We can use that to scan the thyroid then by, now we've made it detectable by putting something there that we can detect, putting the radioisotope there. And so you'll have the scanner move across there, and we can determine the level of radiation and can determine how much is in there, and we can use that to scan and map out the thyroid. We can check sizes, we can check if there's cancerous growth there, we can check healthiness of it based off of how much of the iodine it incorporated, and so on. And so we get a scan of the organ. Here, like I said, is the image of that. The other thing that we can do as well, and I mentioned this story in a prior section where I had a friend who went through this, is a radioactive iodine can also be used to treat thyroid, something like thyroid cancer, by forcing your body to accumulate the dangerous radioactive iodine. And then because radiation can damage cells, and more specifically is going to damage cells that multiply rapidly, which is what cancer is, then we can actually treat it that way. Another type of scan that we can do is positron emission tomography. You can already hear in there the positron emission. We are giving off positrons, and so this is a reaction that gives off the antimatter positron particle that's like an electron, and then because of that we can detect that emission, and so it ends up working in places in the body where there is glucose, just the way that it gets incorporated into your body, and you can see here a scan for Alzheimer's there, and there are different positron emitters that can be used. Here, different radioisotopes that give off positrons, and specifically this one here in the example nuclear reaction equation there is the fluorine-18. And then we can also use other radiations to further map the organs that we're interested in. Computed tomography, or CT scans, are probably one of the most commonly used ones, and they are used to measure how much your body absorbs X-ray beams, and so then we can measure different layers of the body that way, and from there we can predominantly detect fluids and so on, but we can get a scan of different layers, again, organs in the body. Interestingly, MRI, which is probably the most common scanning technology, it is used because it does not involve radioactive stuff, and because of that it is least damaging, and it's actually super safe as long as you don't have metal in your body or on your body. What it does is we create what's called resonance. We force the hydrogen atoms in your body to get excited, kind of like we talked about with the electron configurations. The hydrogen atoms begin to vibrate, they resonate with the magnets. We have certain essentially strengths of magnets, magnetic frequencies that we can do, and we can get them to vibrate in that strong magnetic field, and then they end up, because they're vibrating and moving charges, end up then creating their own magnetic field that is can be detected. And again, we can use this for scans of anywhere in your body that has water. It also can be used to detect hydrocarbons as well, although the water is more likely to react because it's a polar substance versus the hydrocarbons where they're non-polar. And so we can use that to scan different parts of your body. You'll notice on this particular image, we can kind of see the void space where the lungs are. The lungs have predominantly air in them, and so then we're not seeing here the lungs themselves. We're seeing that void space where the lungs are. Not to say that we can't detect things inside the lungs with them, especially if you have, say, fluid on the lung, that would be detectable by something like this. Anyway, those are some of the different imagings. Again, MRI here at the end, it's the most common because it's the safest, but does not actually fit into this topic because it's not actually using radiation. But that finishes section 5.